just to get the main points of the last lecture onto the board, since we're going to be using them today, we're looking now at linear programming. And we talked about formulating linear programs, right? There's the standard form. Where we write min y, min cx such that ax equals b and x is greater than 0, greater than or equal to 0. And also the canonical form, where we write, let me get my letters correct. What do I want to do here? Cx, ax equals b, and x is greater than or equal to 0. And in the canonical form, we have the maximum of yb such that ya is less than or equal to c. Now, I think I said this in the video, but just to emphasize, I'm often a little sloppy about my transposes, so be ready if I suddenly transpose. Hopefully the intention comes through, but feel free to ask if you're not sure which way I'm oriented. So we've got these two different. We've got the standard form and the canonical form, and standard and canonical are kind of synonyms, but we have two things that are both standard and canonical. And we talked about our goal of solving these kinds of linear programs. And as with MaxFlow and min-cost-flow, we're going through a series of steps around first, what are the characteristics of the solution? And then we start talking about how do we test whether a solution is optimal, right? And then we can start looking at algorithms for actually constructing a solution. And last time in Mini, we did this for equalities. Okay, where we're asking for a solution to ax equals b, right? And we talked about the size of matrices in terms of their bit representations. We talked about the sizes of products and sums of matrices and so forth, right? We argued that the determinant of A is polynomial, the size of the determinant of A is polynomial in the size of A, right? And we argued that the implication of that is that the size of the solution is polynomial in the size, I should say the size of, we don't have an optimum here because we're doing equalities. But we concluded that the size of the solution is polynomial in the size of the input. And that's a pretty useful first step, right? To say that there's nothing that stops me from just writing down the solution in polynomial time. If I couldn't do that, then solving it in polynomial time would be hopeless. Was there a question? All right. And we talked about both square and non-square matrices, right? And then to finish up, we talked about verifying optimality, right? So if I'm given a problem ax equals b and told to verify a solution x. That's very easy. I just plug x into the linear system, and I figure out whether x is indeed equal to b. Right? But more interestingly, we talked about how to verify the absence of a solution. Right? And what we said was that exactly one of the following two situations hold. Either there is a solution, right? Or else there exists a proof that there is not a solution. Where you have a vector y such that ya is equal to 0, but yb is not equal to 0. Right? And that's sort of the last thing that we proved. But what this means is, right, that with a witness, you can solve the decision problem. Right? Somebody can either give you an x that shows that the linear system is solvable, or they can give you a y that shows you that the linear system is not solvable. And either way, checking the correctness of that x or y just involves some sums and products. So it's polynomial time. Yes? And that's where we finished up in the video. Okay? So now that we have that basic step, we're going to move on to systems of linear inequalities, which are significantly more complicated. But we will be coming back to these facts about linear systems. They become the sort of infrastructure on which we prove our results for linear inequalities. So, first of all, we're going to talk about geometry. This will be a mathy lecture, right? We might get to some algorithms, but there's going to be a bunch of math first. In terms of thinking in pictures, right? If you have a canonical form linear program, it's really natural to think about that as an intersection of half spaces. Right? Where you have a bunch of constraints, and one side of each of those constraints is feasible. So you take the intersection of all of those constraints, and you get a feasible set. And this is called a polytope. Okay. In the standard form, you tend not to think in the same picture because of the ax equals b constraints. Right? So it's hard to even draw an interesting standard form linear program because one of your constraints has to be an equality constraint, and it only leaves you with one dimension to play with. But if my equality constraint is, for example, this line, right, then the portion of the line in the positive quadrant is the feasible set. Right? In higher dimensions, this is where the drawing gets really disastrous. You can end up with, for example, a hyperplane. Sorry, in 3 dimensions, you might have a plane that is 2 equality constraints, right? And on top of that, and again, that plane, is 1 equality constraint, and that plane is then restricted to be in the positive orthant, and that is the feasible set. Okay. So those are some pictures for you. Some other definitions. we say the polytope is bounded if it's contained in some box. That is, there's some maximum value for all of the coordinates that are in the feasible set, right? So an unbounded polytope might look like this, right? Oh, sorry, it's not a good place to put it. Right, so an unbounded polytope might be, for example, a cone, which can go out to infinity in some direction. Okay? And I mean, already you can see unbounded polytopes might be a problem if you're talking about maximizing or minimizing, right? If there's some direction you can go infinitely far, then there may be no maximum or minimum. Okay? Either of these formulations, the canonical or the standard, defines a convex set, which is to say that if you have any two points that are feasible, the line between them stays feasible, right? Any convex combination of those 2 points is also in the feasible set. Okay. Can anybody argue for the canonical form? Can anybody give a sort of proof by picture for that, or an argument by picture? You can prove this algebraically, but pictures are nicer. Well, let's take the simplest case. Let's consider just one half space. Okay? If I have 2 points that are on one side of a certain half space, then clearly the line between them, I shouldn't say clearly, the mathematicians probably took years to prove this, but the line between them stays on that side of the half space, right? So now can somebody finish the proof? Yeah?
So that's true for all the half spaces, so it must be true for both halves.
Exactly. So you're going to stay, between 2 points, you'll stay on the same side of each half space, and therefore you will stay on the same side of the intersection of all of the half spaces. So you'll stay in the feasible set. Okay? You can also, again, argue it algebraically by saying, well, we've got a bunch of linear constraints here, so the value of these constraints for a point on the line is going to be somewhere between the value of those constraints for the two ends. And therefore, if the two ends are feasible, the value in the middle is also going to be feasible. So these half spaces do define convex sets. The converse is actually also true. Any convex set is actually the intersection of all the half spaces that contain it. Right? So that's true even for things like spheres. You just have to intersect infinitely many half spaces. But we are only going to be thinking about intersections of finitely many half spaces, which create polytopes. All right. So now we have some pictures to work with in our minds. Now let's start talking about the structure of optima. Okay. So if I go back and look at my picture, canonical is always an easier picture to think about. I think I mentioned in the video, standard form is usually better for algorithms. Canonical is much better for thinking. So if I look at this canonical form polytope, and remember we showed last time that you can transform between them. So you can work with either one. So I'm going to think of this. Where in this picture, where are the optima going to be for various objective functions? Yes? The vertices of the polytope. And what is a vertex? Good. So you're saying that the optima are going to be found at the places where two of the constraints of this two-dimensional linear program occur. Now, is that the only place that optima can be found? Yeah?
We might have a case that we have an optimum along an entire line, but that will
True.
also include the endpoint. So
Good. So sometimes, right, if your objective function is perpendicular to a boundary, then the whole boundary might be optimal. Okay? But you'll notice that the boundary is going to include some of these corners. Right? And so there's a sense in which these optima can always be found at corners. Right? So I will claim that optima are always on the boundary. You can't have an optimum that is off the boundary. Right? Or sorry, let me put it a different way. All the optima are on the boundary. You can't have an optimum in the middle of the polytope. How come? Yeah?
So the constraint, if you're thinking canonical, for example, like YB is a line, so you can just keep on going into the direction that makes it greater until you get out of the...
Great. So the point is that the middle of the polytope is a place where none of the constraints is tight. Right? And so that means you can move a little bit in any direction. And in particular, you can move in the direction of the optimum. And you can keep moving in the direction of the optimum until you hit a constraint that becomes tight. Now you're on the boundary. Okay? But the stronger point is that an optimum should exist on a corner of the polytope. But now we have to define what corner means. And it turns out there's actually 3 different definitions of the corner of a polytope. And so you said vertex, but you described what is not actually called a vertex. So now some definitions. A vertex is a point that is not, is a feasible point that is not a convex combination of 2 others. Okay. Now, another definition that's interesting is what's called an extreme point, which is a point that is the unique optimum for some objective. Okay. Now there's a third definition of what's called a basic solution. A basic solution is one where all the equality constraints are tight, and in total, n linearly independent constraints are tight. Okay. And now we refine this with our final definition. A basic feasible solution is one that is basic and feasible, surprisingly. Okay. Yes?
Dimension of the space?
Yes. N is going to be the dimension of the space for at least the next week. Okay. Yes?
How come a basic solution is not feasible?
A basic solution might not be feasible because, let's see, what's a good picture I can make here? So here is our polytope. okay? Here is a basic solution that is not feasible. It is the intersection of two linearly independent constraints, and there are no equality constraints here. Right? This is like a canonical form LP. Well, any intersection of, let's see, this is violating general position. I have 3 lines hitting at a point, but all of the intersections of two, here what I have is 3 constraints that are not linearly independent, right? But any 2 of them form a basic solution. So all of these are basic solutions, right? But not all of them are basic feasible solutions because some of them are outside of the polytope. They violate some other constraint that's different from the ones that form the intersection.
So when you say nonlinear independent constraints are tight, it basically means intersection.
That's right. A tight constraint, it's a good question, right? If a constraint is tight, it means that your point is on the hyperplane, right? And so if n linear constraints are tight, it means that your point is on n different linearly independent hyperplanes, right? And what does that mean? It's at the intersection of all n linearly independent hyperplanes, and that means it is specifically defined, right? There's only one point that is at the intersection of n linearly independent hyperplanes. And if I just tell you the hyperplanes, you can actually compute that point, right? How do you compute the point that is at, what sort of algebraic operation do you perform in order to compute the intersection point of n linearly independent hyperplanes? You would use the determinant in order to find the answer, but how do you actually say, I want the point x that is at the intersection of n linearly independent hyperplanes? It's a system of linear equations. It's ax equals b, right? Everybody see that? Yes?
Could you provide some intuition for the difference between vertex and extreme point and a basic solution?
But you see, this is what's interesting. Now that I've made all these definitions, these are all exactly the same. Okay? So these are 3 different ways of characterizing the corners. But you can prove that they're actually all identical. In other words, that a basic feasible solution is, in fact, not a convex combination of 2 points, and it is the unique optimum for some objective, and all of the other implications. Okay, we have 3 if and only ifs here. And this requires proof, and since this is not a math class, I am not going to prove these things ultra rigorously, okay? But I'm going to sketch some of the arguments because they have implications or give intuitions for some of the algorithms that we're going to be developing, okay? They're not really hard to prove, but we also don't have a lot of time, so I'm not going to do all of the details, okay? So let's look at a few different directions. First of all, actually, let me go one direction at a time. That you have a basic feasible solution if and only if you have a vertex. Okay. So let's go in one direction. If your point is a convex combination, in other words, if it's not a vertex, okay, what does it mean? It means that there is a line, that there is a feasible line through it. Right? So every point on this line is feasible. Now, if this point was the intersection of n linearly independent constraints, that were tight, right? Could you have such a line? How come? The point is that if you have, sorry, yes?
Well, then I would say, well, then if we have this line where we can move in both directions, at least a bit, then our constraints could not be tight because, well, we can change basically towards making them tighter.
Exactly. The point is that moving in any direction will violate a constraint. Okay. Sorry, that's not correct. Moving on any line will violate a constraint in one direction. Okay, so again, the 2D story, right? We've got this polytope. Here I am at the intersection of two linearly independent constraints, right? Now, if I draw any line through this intersection, right, part of it goes into the polytope and stays feasible. But in the other direction, I go out of the polytope. I can't move in. There's no direction that will keep me feasible for all n of the tight constraints. Okay? Or to put it another way, right, if I have fewer than n tight constraints, then their intersection forms, say, a line. And everything on that line is, I can move on that line and stay tight for all of those constraints, and therefore I won't violate any of them. Right? But as soon as I put in one more constraint, that cuts the that stops me from moving in one direction or the other on the line. Okay. And that actually is the converse, right? Right. So this says that if I'm not a vertex, then I am not a basic feasible solution. If I am not a BFS, that means that there are fewer than n tight constraints. And that means that their intersection is a feasible line through the point, or a feasible plane or something. But there's a greater than zero-dimensional feasible space defined by the intersection of these tight constraints. Yes? And so if you have a feasible line through the point, you move a little bit in each direction, and that gives you 2 points whose convex combination is your starting point. Yes? Okay. The last one is the extreme point. Okay. Sorry, my notes got a little scrambled here. So remember, an extreme point is a unique optimum in some direction, right? So if you're an extreme point, that implies that you are on a basic feasible solution. Because, or sorry, is that backwards? Yeah, what's going to stop you from moving to another optimum is the question, right? So if your point is not extreme, if you so if your point is extreme, if you cannot move towards any other optimum, right? Imagine, if there was another optimum, there would be a line between your optimum and the other optimum, right? And then you could move on that line through what would be various other optima, and that would all have to be feasible, so that would mean, just like in this argument up here, that you don't have n-tight constraints, right? So that tells me that if you're not an extreme point, then you are not at a basic feasible solution. So actually it goes this way, right? Conversely, or sorry, to put it in another way, that's the intuition, but the sort of math is that if you're at your BFS, you can let if you look at the standard form, you can actually fill in some math here. What you do is you let T be the set of tight xi greater than or equal to 0 constraints. So remember, in standard form, you've got the equality constraints, and then you have, in addition, non-negativity constraints. The equality constraints are always tight at a BFS, but you also have some of the inequalities tight at a BFS. And then if you set the objective to be the sum of these xi's, then you get a direction for which this basic feasible solution is the unique optimum. Okay, because if you move if you move farther in this direction, right, in order to make this larger, right, or sorry, in order to make this smaller, because this is a minimization, because it's a standard form LP, right? In order to make this smaller, you're going to have to make one of the xi's smaller, and they're all already tight. So you can't do it. Okay? So again, this is sketchy, but it's the core of the argument for why a basic feasible solution is also an extreme point. Okay? And conversely, if you do have an extreme point, if it's a unique optimum, then if you think about why there aren't any other optima, right? The answer is that there have to be n-tight constraints that prevent you from moving, because otherwise there's a direction in which you can move where things will stay good, right? So if I have an optimum here, right, and it's unique, right, that says that any direction I move in which improves the objective function has to make me infeasible. So, right? So again, any line through this point, one of its directions has to take me through a constraint, right? And the only way that that can happen is if you have n-tight constraints, because if there's less than n-tight constraints, then there's a line on which you stay feasible, and in one of the directions of that line, you're not going to get worse in your objective function. Okay? So again, saying that more rigorously requires more time than I have, so I'm not going to. And if you are sort of concerned, you can sort of set all of that aside and say, these are just three things that happen to be identical. You can take that as a given as we go forward. Now, as I was saying before, an immediate corollary of this is that the optimum, let me write it over here. Corollary of this is that the optimum of any LP has polynomial size. Why is that? This is, again, good news for our hopes of coming up with an algorithm. Yes?
Is it because all the basic feasible points are polynomials, right?
Exactly. A basic feasible solution satisfies ax equals b for some subset of the constraints. And we already proved last time that every linear system solution has a polynomial size, right? So this is good. This is the first really important result for our linear inequalities, is that you can write down the answer. Now there's another corollary that's also interesting. Any standard form LP with an optimum has one at a basic feasible. Sorry, I shouldn't write this as a corollary. This is more about an algorithm. So I argued over here that these are equivalent, but now let me give you an algorithmic reason that we can equate these. Okay? So suppose we have an opt that is not at a basic feasible solution. Okay? I want to demonstrate that there is also an optimum at a feasible solution. How can I do that? So what does it mean that I am not at a BFS? Yes?
So you can move along some lines in both
Right. Right? So if I'm not at a BFS, that implies that there are less than n tight constraints okay? Let's call this optimum x that is not at a BFS. So that means that there are less tight than n tight constraints at x. And that means that there is a feasible line through x. Right? Now, what happens to the objective function as I move along this line?
So it's either a decrease or
Are those the only two possibilities? Right. So if I move in a direction along the line, then the optimum will increase or decrease or stay the same. Okay? Now, again, this is standard form, so it's a minimization problem. Right? So what does it mean if it decreases? Yeah? Right. If it decreases, then we didn't start at the optimum. Right? So that can't happen. Okay? So if there's a decrease, that implies we're not at the optimum. What if it increases? Yeah, sorry, a question? Okay, what if it increases? Right. If there's an increase, that implies that the opposite direction decreases. And we just said that that can't happen. So, in fact, the objective is going to be unchanged as we move on this line, which means that, in fact, all of the values on this line are optimal for the objective. Okay? That means we can move in either direction and stay optimum, right? Okay, which direction should we move in order to help our proof? Yes? It actually does. There's one direction. We want something to happen. So again, we are currently not at a basic feasible solution. We don't have enough tight constraints, right? So we want to make more tight constraints. So which direction should we move in? Yes?
We want to reach a BFS, so we need to move to the direction where we satisfy a non-tight equation.
Right. We need to make a not tight constraint tight. Now, in standard form, all the tight constraints are xi greater than or equal to 0. So if we want to make one of those tight, what should we do? Yes? Make it 0. And so how are we going to do that? Well, we are feasible, right, which means xi is greater than or equal to 0. And so the way to make it 0 is to decrease it. Right? So what we're going to do is we're going to move to decrease some xi. Right? As you move on this line, each xi increases or decreases, or maybe it doesn't change, but it's a line, so the xi's can't all stay unchanged as you move. Move in a direction that decreases one of them, and eventually either that one will reach 0 or some other xi will reach 0, and then you've just created another tight constraint. Okay? So when some xj drops to 0, you get a new tight constraint. And you can repeat this, right? Each time you do this, you get another tight constraint. And so after at most n of these steps, you will have algorithmically generated a basic feasible solution from whatever optimum you started at. Yes?
So let's say that you're at an optimum, which means that moving in any direction won't change your objective function, right? But doesn't that mean that literally everywhere it's the exact same value for the objective function?
Well, not everywhere, but everywhere that is the intersection of your current tight constraints. Right? So remember, what we're saying here is that there is a feasible line through x, and everywhere on that line, the objective value is the same. There are a lot of other points near x which might have different objective values, but we're only concerned with the line. All right? So any questions about this? All right, so I've got one. Why did I say that any standard form linear program with an optimum has a solution at a basic feasible solution? Yes?
We can convert any LP to standard form by adding slash variables or
Yes?
some sort of.
Well, so that's true. We can convert any linear program to standard form, right? I showed you that in the video, right? And once we do that, there will be a solution at a BFS, okay? But what about before we convert it? Like, why didn't I just say that any linear program with an opt has a solution at a BFS? Well, I didn't say it because it's not true. Okay. So a really annoying example is the canonical form linear program, minimize 0x plus 1y, subject to the constraint that y is, sorry, maximize. Yeah, that's right. Subject, sorry, it's been too long since I've done linear programming. Canonical form is maximize. Subject to y being less than or equal to 2. Okay. What does that canonical linear program look like? Well, it puts a y less than or equal to 2 ceiling and then says, I want to maximize my height. Right? So where is the basic feasible solution? There is none. Right? There is none because there aren't two constraints to intersect. There's only one. Right? And essentially every point on the constraint is optimal. Okay? And this really is why algorithmicists like standard form. Right? Again, mathematicians like canonical form because it's pretty. Right? But algorithmicists like standard form because you can talk about basic feasible solutions. And it is informative, if you want to take the time, to translate this to standard form and see how a basic feasible solution appears. Okay, so that's an exercise that you can do. On the other hand, if the optimum is unique, then it is a BFS. The only way things can go wrong like this is if your entire boundary or some entire boundary is an optimum, and that means that you've got infinitely many optima. Okay. Also, if the polytope is bounded, then there exists an opt at a BFS. So it doesn't have to be in standard form, but it does have to be bounded. And again, standard form isn't always bounded, but standard form can be, the way we proved it was to rely on the bounding effects of the positive orthant. And you can use any boundary. The idea is that if you're not at a basic feasible solution, there's some feasible line, you move on that line. If you know you're going to hit a boundary, then you know that eventually you know that you're going to hit a constraint before you hit that boundary, because that's the definition of being bounded. So every bounded polytope actually has a constraint at that is a basic feasible solution. Okay. All right. So we've now got these nice corollaries that, there's always a solution at, the solution is always at a BFS. It's always feasible to write it down. In fact, this also gives us our first linear programming algorithm. Right? An actual series of steps that you can perform to solve any linear program. Okay? We haven't developed much machinery yet. Can't be a very sophisticated algorithm. But how would you do it, knowing what you know about linear programs? Which at this point really is just that the optimum is at a basic feasible solution. Yes?
Force your way through the BFSs.
Exactly. Try every BFS. Okay. So it's like we're back in elementary algorithms. The solution is BFS, right? So what's the runtime? how long does it take me to try one BFS? How would you do it?
Plug in the you just plug in what is CX.
Well, in order to plug in what is CX, in order to compute CX, I need to know X. What do I need to do in order to figure out X? Yes? I have to solve a system of linear inequalities, right? So a BFS is defined by a set of n-type constraints. So I say, maybe these are the n-type constraints, right? Once I know what the constraints are, I can solve the linear system, right? And that gives me an x, and then I plug that x in, and that gives me the value of the objective at that BFS, right? So pick n constraints, solve ax equals b, right? It may turn out that the n constraints that I picked aren't linearly independent, right? But that's okay. In that case, I will simply, sorry, I think I may actually have had this upside down. A sec. No wonder it's giving me a headache. That's better. So the constraints might not be linearly independent, but then in that case, it's not a BFS, so I wasted my time trying it anyway. And then I can compute CX. Okay. So testing one basic feasible solution is the time it takes to solve a linear system, which is Gaussian elimination, which is n cubed or so, right, in n dimensions, right? This is ignoring the sizes of the numbers. Okay. So it takes n cubed time to do them. So the question then is just how many of these BFSs are there? Yeah? Oh, go ahead.
How many constraints are you allowed to have? Just generally as many as you want?
In a linear program, so again, I said that n is the dimension, and we're going to use m for the number of constraints. And that's arbitrary, right? You can write down as many linear constraints as you want, and you get a linear program. Now, as we've just been discussing, at the end of the day, only n of those constraints matter, right? All of the others are redundant to the problem because they don't change the optimum.
So would it be m choose n?
Exactly. If there are m constraints, then you just go through picking m choose n possible basic feasible solutions. Yes?
You also have to check whether there exists an optimum.
Well, as I test the basic feasible solutions, right, I see what you're saying. Let's see, what do I need to do in order to know that there isn't? Well, if I do find an intersection of n linearly independent constraints, so if my polytope is unbounded, there might be no optimum. We will I believe that you can tackle that at the same time, but we're going to address it in a few minutes, so let me defer that particular issue, okay? We want to choose n of m constraints, and then we spend n cubed time testing them, right? So the overall runtime is about m to the n times n cubed. Okay. So actually, this is not, it's pretty bad, but there's a place where this is not terrible, right? If your dimension is small, right? If you're doing linear programming in 2 dimensions or in 3 dimensions, this is polynomial. Okay? Yes?
So if we search for a BFS in the standard form, there's always a BFS.
Correct. If you convert it, oh, sorry, thank you. This algorithm, right, if you apply it to a standard form linear programming program, we just argued that there always is a solution at a BFS, and that means that you will find it this way, right? If you search all basic feasible solutions of, say, a canonical form, you might not find the optimum because there might not be one at a BFS.
But you might not always want to convert to standard form because if your dimension was originally constant, it might no longer be.
Correct. On the other hand, as I said, if you're an algorithmicist, you really want to convert it to standard form because they're so much nicer to work with. OK, so that's great. We have now achieved our first algorithm. And that's probably a good time to take a break. OK, so let's take 2 minutes. And then we'll start working towards better algorithms.
I've done my second T-set, how do I submit it? It's already past the last
Check with Will over there.
Yeah, there. One in the sixth row.
What?
One in the
Yes. Yes. Everybody's sitting. That's a bad sign. We may have to cancel the break early. Do I need to start bringing some dance music to get people moving during the break? All right, let's resume. So we've now talked through the structure of Optima. We understand a lot more about what the input problem looks like and what the output optimum looks like. So the next step is going to be about verifying optimality. Okay? So again, if I give you a linear system, you can just check, does AX in fact equal B? But if I give you a linear program and say, this is the optimum, this seems much harder, right? Because yes, I can certainly check that AX equals B and X is greater than or equal to 0, but how do I check that this is the minimum possible objective over all of the other possible feasible points, right? You can also frame this as kind of a decision question, okay? So I described linear programming as an optimization problem, maximize or minimize the value of the objective. You can also ask a decision question, right? Is the value of the objective greater than so and so? And we have proven that the decision problem can be verified in polynomial time if the answer is yes. Right? You can be given the optimum, and that will prove that the optimum is greater than or equal to a target value if you have a maximization problem. Right? But how do you prove that the answer is no? Right? How do you prove that there is no value whose objective is larger than a certain target? Okay. So this is the analog of how do you prove that there is no solution to a linear system. And we're actually going to leverage that in order to do linear systems of linear inequalities, right? So the motivating question here is to ask, if I'm given a particular solution, how do I prove that there's no better one? And this is going to let us introduce the notion of duality, which is really the center concept of linear programming and a lot of other things. It's the sort of strongest result in the theory of linear programming, and it's going to allow us to give a succinct and easy-to-check proof that a given point is optimal for a linear program. Okay? And so it's going to give us a succinct proof of optimality. And just as special cases, it's going to give you max-slow min-cut. And it's going to give you the feasible prices formulation for min-cost flow. It's going to give you the results on Nash equilibria in two-player games. Lots of other stuff. Okay. The starting point is we're given a, let's say, canonical form LP. We want to minimize CX such that, a standard form LP, such that AX equals B and X is greater than or equal to 0. Okay? Standard form linear program. Okay? Now, this is a minimization problem. So how do we prove that you can't do better than a certain value of the objective? Well, we want a lower bound on the optimum. Right? If we lower bound the optimum, we're showing that you can't do better than a certain value. If we're then able to find a point that matches the lower bound, we know that that point is optimal. Yes? So how can we construct a lower bound that applies to all the feasible points in this linear program? Right? So a feasible point is a point for which AX is equal to B and all the x's are greater than or equal to 0. What kind of lower bound applies to all of them? Well, one thing we can do, this is like substitution in algebra. Imagine if we try to multiply each constraint, AIX greater than or equal to BI, by some positive YI. Actually, it doesn't have to be positive. Let me, by some YI. And then adding up the results. Okay? So I have AIX equals BI, therefore I have YI times AIX is equal to YI times BI. And now if I add them up, right? If I now sum all of these up, it turns out that in algebra, we have that YAX equals YB. Okay? I'm basically multiplying the left and right sides by some y. Okay? And since we have equality, the results are also equal. Okay? But now, if ya is equal to c, okay, and this is coming slightly out of thin air, then yb is going to be equal to y times ax if x is feasible. Right? Because for a feasible point, ax is equal to b. Right? But we already said that y is equal to c. Right? So what would that mean? If we did find this kind of y, if ya was equal to c, so that yb was equal to cx for every feasible point x, right? What would that imply about our starting linear program? Yeah? Right. It means that all points, all feasible points, have the same objective cx, which will be equal to yb. In other words, every single point will be optimal. Yes? But that we can only conclude if we're somehow able to find a y such that y is equal to c. Okay? So then we have, like, it's much stronger than a lower bound. It's an everything is equal bound. Okay? But we can't always find this because it's not always true. But we could generalize that idea to get a lower bound. Okay? What we can ask for instead is, suppose that we just find a y such that ya is less than or equal to c. Okay? If ya is less than or equal to c, what can we conclude by applying the same analysis as I just did for the equality case? Yes? How come?
Because, like, if you multiply x is all positive, so, like, if it's less than
Exactly. That's what's crucial. You use the fact that all of the x's are positive. Okay? Because now what we can say is that yb is equal to y times ax, right? Which is equal to ya times x, right? Which is less than or equal to cx because all xi are positive. Okay. And of course, here I'm talking about is for feasible x's. Right? In other words, we have a lower bound. Okay? We can conclude that yb is a lower bound on opt. Okay? Yes?
Can you repeat what you are doing for the dashboard, for the duality board?
Yes. So what I'm arguing here, sorry, I mean, the previous board was just leading up to what I'm saying now, right? So this is the board where I'm doing the actual work. I'm saying we want to find a lower bound on the optimum. So if we can find any y such that y is less than or equal to c, then we get a lower bound. Why do we get a lower bound? Because yb is going to be less than or equal to the value of the objective for any feasible x. Okay? And that's for two reasons. One is that for a feasible x, ax equals b, so I can do this substitution. And the other reason is that for a feasible x, x is greater than or equal to 0, which means that when y is less than or equal to c, right, coordinate by coordinate, you now multiply each of those by a positive value. And so all the left multiplies are smaller than the corresponding right multiplies, which means that now when you add them up in your dot product, you get something on the left which is less than or equal to something on the right.
So what does it mean that we have a lower bound?
Well, it means that we have a lower bound, right? So again, we're trying to prove the optimality of a particular point. Right? So somebody's given us a particular x and said, this is the optimum x. So one way to prove that optimality would be to give a lower bound that is achieved by that x. Right? If you get a lower bound that's achieved by that x, you know that that x is optimal. Okay?
So where does the y come from?
Well, that's the question. If I want to give the best possible lower bound, what y should I use? What do I want to do to get the best possible lower bound? Y is a vector. I can't maximize it. Yes? I want to maximize YB. Right? Every y that satisfies this equation, this inequality, is a lower bound. So if I just look for the largest possible lower bound, I can do that by maximizing YB. Okay? In other words, what I want to solve to get the best possible lower bound is max of YB such that YA is less than or equal to C. What's that? That's a linear program. Okay? So in order to get a lower bound on my standard form linear program, what I do is I solve a canonical form linear program. Okay. Now this canonical form LP is known as the dual of my starting linear program, the minimum of Cx such that Ax equals b and x is greater than or equal to 0. Okay. And if you think about it, we have just shown, we've actually proven weak duality. Which is the statement that the optimum of this linear program is a lower bound on the optimum of this linear program. In other words, this optimum is less than or equal to this optimum. Okay. But you notice we've also proven something else. We've proven that this linear program is an upper bound on the optimum of this linear program. Okay? And so, in fact, these two linear programs are declared to be the duals of each other. Okay? It's a symmetric relationship. And each of these linear programs provides a meaningful bound on the value of the other linear program. Yes? So I said we have just proven weak duality. Okay? They are bounds. Next time, we will prove strong duality, which is that under some very minor restrictions involving boundedness, these two optima are equal. Okay? And that is linear programming duality and sort of the crux of the pivot of linear programming. Okay? This is used in analysis all the time, and it's also used in the design of algorithms for linear programming. Okay. You can do a little sanity check for all of the definitions I've been throwing around. You can show that the dual of the dual is the primal. Okay. So, sorry. This other linear programming is called the dual. The program that you start with is called the primal. Okay. And again, it's symmetric. So depending where you start, you generally call one the primal and the other the dual with the appropriate context. All right. And we'll start with this next time. We'll do this little sanity check we'll do the math to show that if you take the dual of a linear program twice, you get back to where you started. Okay. Now, in order to do that, we're going to have to talk about duals more generally, right? So here I've only told you about how to take the dual of a standard form linear program. So we will generalize this to talk about the dual of an arbitrary linear program. And I'll show you how to transform any linear program into another LP that bounds the first LP, a dual. And our strong duality result will be that for every such transformation, you get equality in the optima. Okay? So, any questions about that? All right, so next time, what day of the week is it? Let's see. Friday. Friday will be our duality lecture, where we actually prove strong duality and start to use it for some really fun results, like maximum min-cut for free. Look for a problem set to be posted later tonight, which will give you a lot of practice with linear programs.